Okay, so back where we were. So again, we're just going to go about a half hour, and then I'm going to stop. And then you guys at home, you can stay if you want, but then you guys would be dismissed. Can you guys at home see this slide?
Yeah.
We're good? Okay, thank you, Alan. Okay, so just real quick, if you guys watched, I posted a lesson on Friday, and I talked about this. And where we're going now, I've told you we have covered now the main points in Chapter 12, which is the differential rate law, the ratios to figure out the order of reaction. The integrated rate law, where we do graphs to figure out the order of reaction. But now we're going into the last part of the chapter. And here is going to be actually a third way. And I'd say this is the third point. And it's not as big a point, but it's definitely fair game for our practice. I mean, for our quiz, our labs, our test, and the AP test. But it's going to be activation energy diagrams, which I'm going to talk today, and reaction mechanisms, which is where you have a series of reactions and you can total them up. A lot like what we've done already back in when we did redox reactions, as well as when we were doing the delta H calculations a little bit. So it's still something, that's why I want to make sure we cover it. And this too is going to be something that in a normal year, these activation energy diagrams, not that it's that confusing of a topic, but in a normal year, we would have covered these in the previous year, in the spring of the previous year. But of course, last spring was far from normal. And so I want us to spend a little bit more time. Because again, and that's actually what's on the screen now, is an activation energy diagram. So I talked about this, but I want to just again, one more time, emphasize this. So notice what it says too, that colliding molecules must have a minimum amount of kinetic energy or activation energy. EA, capital EA is activation energy. So again, I said this in the lesson that I posted on Friday, but you should note this. So for a reaction to occur, three things. For a reaction to occur, number one, molecules have to collide. Okay, molecules have to collide, number one. Number two, they have to collide with this minimum amount of energy called the activation energy. Okay, so number one, molecules have to collide. Number two, molecules have to collide with this minimum amount of energy called the activation energy. If they don't, the reaction will not occur. And then number three is the molecules have to be oriented correctly. They have to come in so they're oriented right. So molecules have to collide, they have to have a minimum amount of energy, and they have to be oriented correctly. Something to remember. Okay, so here is kind of where I left off a little bit. Something I did talk about, but I want to go over it again because this is, again, it's something that's definitely on our test, it's on our quiz, it's on our lab, and something I think will be on the AP test. This is called an activation energy diagram. So I'm just going to kind of talk for a little bit, connecting it to the diagram. And again, this is something that would have normally have been reviewed from first year Chem. But because last spring, everything was so weird, you know, if you were following along, you were doing it. I guess that's one thing. We're doing these remote things better than we were back in the spring. That was quite a wild time. But activation energy diagram. First of all, know what's being graphed. On the y-axis is energy, and on the x-axis is time. Okay, there are 5 key points on this graph. Okay, the first one, and this is the way the graph looks. So right here, point number 1 is the reactants. I'll just write it in there. Okay, and if you notice what's on the slide on the overhead, it says the same thing. It says the reactant. So that makes sense. Remember, reactants react. That's where you start. So that's the first thing. Okay, number 2 over here are the products. And again, now that you guys have been through almost God, this sounds horrific. A year and 3/4 of chemistry. You kind of got this vocabulary down. Reactions we start with, products we end with. So reactions we start with, products we end with, and you can see that again on this slide. The very top of the graph is called the activated complex. And the way these work, these graphs, these activation energy diagrams work, it's kind of like when my wife is an excellent skier. She loves to ski. And two of my sons, they love to snowboard. But one place my wife loves to go is to go to Mary Jane and to Winter Park. It's probably her favorite place to go. And I have actually, there's this run called Sleeper. I used to really enjoy it. Of course, it's not a hard run because I'm not very good at it. But it was kind of a steep run, but it wouldn't have any moguls on it. All that being said, to get to Mary Jane Winter Park, you got to go over Bertha Pass. There's a peak. There's a barrier you got to go over. Well, that's kind of the way this is the activated complex would be the very top of the pass. Okay, then kind of the whole thing is what this is all about is the difference between the top minus the start is the EA. And EA, this is 0.4. This is the activation energy. It's the activation energy. It's the energy barrier. And the bigger the energy barrier is, the bigger the activation energy is. And this would be worth noting. The bigger that the activation energy is, the slower the reaction is going to go. The bigger the activation energy, the slower the reaction is going to go. And the smaller the activation energy, then the reverse, the quicker it's going to go. Here in a minute, I'm going to show you this YouTube, two pretty short YouTube videos that are going to show you this really reactive compound called nitrogen triiodide that even, I'll show you in one video, even with a balloon just touching it or with a feather, it'll react. So it's going to have a really low activation energy. So activation energy is always equal to the top minus the start. So it's the difference between these. And so here, and if you look on this, what's on the slide, talking to you, those of you at home, so when it's in the top right-hand side where it says the activated complex, and it says EA question mark, that's the activation energy. Well, on the graph, it says, on the left side, it says EA forward, it's 209. And so the question mark then would be 209 kilojoules. Now, on a graph, if they just give you the graph and they go, okay, here's 200, and then here is 409, you just subtract those two and you know it's 109. Okay, so the reactants where you start, the products are where you end, the top is the activated complex, and the activation energy is the top minus the start. The final thing, number 5, is going to be the difference between the ending and the beginning. And that is called delta H. So here we go back to stuff that we talked about back in the fall. Chapter 6, thermochemistry, another way to solve for delta H. So here it is the ending minus the start. Or, really to be more correct, it's the products minus the reactants. And if you look at this, so if we do the products minus the reactants, the products are a smaller number than the reactants, which means this is going to be negative. So, and if you look right in the middle of the graph, it says delta H is negative 139. So the delta H, where it's in the upper right-hand corner, the delta H question mark would be negative 139. Okay, so reactants 1, products 2, activated complex. The activation energy is the top minus the start, and the delta H is the ending minus the beginning, or products minus reactants. Now, if a problem said the reverse reaction, what would be the activation energy for the reverse reaction? We're going to talk a lot about reverse reactions starting probably Wednesday when we talk about equilibrium, would be going this way. So the activation energy for the reverse reaction, so the EA for the reverse reaction, RXN reaction, would be the difference between these two. That would be the activation energy for the reverse reaction. And so where it says what would be the activation, so underneath the graph, when it says what would be the activation energy diagram for that reaction, well, that's the reverse reaction. And then, like I said, activation energy, EA, is an energy barrier that prevents less energetic molecules from reacting. So if I showed the diagram for the reverse reaction, it would look like this. So this would be this diagram. This would just be the reverse reaction. Okay. And this reaction, because it's for the delta H, this would be the delta H right here, and this time it would be positive. Remember, when the delta H, if it's negative, which this reaction is, it's exothermic. Remember, exothermic means it's giving off energy. So this reaction would be endothermic because the delta H is positive, because the ending is above the beginning. Okay, I want to show you guys a short YouTube. There's two. One of them's a little bit longer. It's like, I don't know, 4 minutes long. And the other one's like 30 seconds. So it's really fast. This is this reaction of nitrogen triiodide. And they even kind of explain why it's so reactive. But it's kind of a cool reaction to watch. And then I want to talk about, when we're done watching this, what would an activation energy diagram look like for this reaction? Okay, so here we go. Okay, can you guys at home see this guy with the blue ear muffs on?
Yeah.
Okay, thanks, Alan. I know Alan's listening. I wonder if anybody else is. Don't answer that question. We know the answer.
It's always good to start a video off with a bang, and there could hardly be an easier way of doing that than with this stuff. What we have here is a contact explosive called nitrogen triiodide.
So fun to do.
It's a highly unstable substance that detonates when disturbed. Now, you might have heard of nitroglycerin, which is another kind of contact explosive, which goes off when you hit it with a hammer. But this stuff is in a league of its own. Even something like a mosquito landing on it will set it off.
Very reactive.
Now, the reason this compound is so unstable is all down to how it's put together. Now, it's nitrogen triiodide, so we have a nitrogen atom, and this is a trivalent atom. That means it likes to form 3 bonds with other atoms. So when we bring it together with iodine, it forms bonds with 3 iodine molecules, and they all go on this side of the nitrogen atom because of the way that the nitrogen's electrons are arranged. So, so the iodines all go on over here, and you can kind of see there's a bit of a problem here, which is that there's not a lot of room for all these iodine atoms. They're much bigger than the nitrogen atom, and so they're all kind of squeezed together and all repelling each other. And this creates something called bond strain or steric strain, which makes the whole molecule less stable than you'd expect it to be, given the components. Now, chemists would say that this results in a low activation energy for the decomposition of this molecule. Everyone else would probably say that it's liable to fall apart. One of the characteristic products of this reaction is the beautiful plume of purple iodine gas. And you can see this again if I chuck this tiny piece of solid iodine onto this hot plate.
The iodine gives off that purple.
Now, this iodine is formed along with nitrogen gas as a result of all those triiodide molecules falling to pieces and recombining into a different arrangement. And it's this recombination that releases all of the energy, setting off more triiodide molecules and more in a chain reaction that races through the rest of the substance, decomposing all of the molecules and releasing a huge amount of energy in a tiny fraction of a second. we filmed this same reaction with a high-speed camera so that we can see just how fast it really is. Here are 37,000 frames a second. And again, a whopping 59,000 frames a second. Even at this highest frame rate, we can see that the reaction occurs across just a couple of frames. To go that fast, the shockwave that's propagating through the reaction must be traveling at a couple of miles per second. That translates at around 7,000 miles an hour. And that's actually about what we would expect to happen, because after all, this is the propagation of a disturbance. In other words, it's the movement of a sound wave. As this is an acoustically propagated reaction, we should expect it to proceed at about the speed of sound. But not the speed of sound in air, but a much faster speed of sound in the solid Ni3 crystals. And the speed of sound in solids is generally in that ballpark, a few thousand miles an hour. Finally, when we played back the slow motion footage, there was one other thing that we saw. If you look carefully, you can see, maybe just for a frame or two, that the triiodide flashes as it detonates. And you can see this on both of the videos. Now, I'm not sure exactly what the cause of this is. It happens far too fast to see with a normal camera or with a naked eye. I suspect it might be a result of all that heat being produced by the release of such an enormous amount of energy in such a small space in a short period of time. And then that heat dissipates incredibly quickly as the gaseous products expand. But maybe not, though. If you have an alternative explanation or some suggestions for how we might investigate this, then drop them in the comments below. Otherwise, that's all for now, and I will leave you with a triiodide super montage.
A super montage. Just touch it with just a little straight. That looked fun. Okay, and then here's just it's the same thing. Let me just show you this. It's kind of fun. This guy just touches him with a feather. He's got, well, here you can see there's like 3 or 4 of just filter paper with this nitrogen triiodide.
So anyway, we have nitrogen triiodide set up on 5 pieces of filter paper here on the ring stand. And if it does what it's supposed to,
oh my gosh, chemistry is so fun. Okay, so now back to what we were doing. Okay, so I'm going back to the notes, guys. So, Alan, tell me if you guys can see. Can you see those notes now, Alan?
Yeah.
Okay, perfect. Okay, so now back to what we were talking about, activation energy diagram. So what would an activation energy diagram look like for the nitrogen triiodide? So what kind of activation energy does it have? Very, very, very small activation energy. And then was that an endo or exothermic reaction? Remember, endo would take energy in, it would get colder. Exo would give energy off. Very exothermic, right? So it would look, so again, if I had energy here, I had time here, this is the EA, the activation energy for the nitrogen triiodide. It would look like this, and it would have a really low activation energy, a really small bump, but then it would be extremely exothermic. So if I ask you to sketch a diagram like that, something that's very reactive and have a very small peak, be extremely exothermic. Okay, next slide. Let me just talk about this. This is not a huge thing, but this is what's called a Maxwell-Boltzmann diagram. So what is being graphed here, if you look at this, is number of collisions on the y-axis, energy on the x-axis, and we have in blue T1, which is colder, and in red T2, which is warmer. And the key thing is where it says EA on the x-axis. If you go up, notice that T2 is higher, which means what this is showing, what this graph is showing, is when the temperature goes up, more molecules are going to have the required activation energy, which means there's going to be more collisions. So again, what I would ask you guys to do if I gave you a diagram like this, or if they gave you one like this on the AP test in May, is to interpret what is this graph, what's it saying? And again, what it's saying is that dashed line for activation energy, the warmer temperature sample has a higher number of molecules or collisions which have the required activation energy. So the minimum kinetic energy for an effective collision, a higher percentage of molecules has sufficient kinetic energy at higher temperature to react. So a Maxwell-Boltzmann diagram is really, it's just interpreting what the graph is saying. Okay, and then I'm going to skip a few pages here. I'm going to go through these. I'm going to just give a minute for those who are taking notes. That's a good thing if you're taking notes. But there's going to be something here, which again, years ago, 7-8 years ago, before they kind of revamped the AP chemistry class, they used to have this next equation on there. But they've taken it off, and it's not on our test. It's not on the AP test. But I'm just going to put it up just briefly. And it's going to show you something, again, if you take chemistry beyond our class, something that you might get into. It's called the Arrhenius Equation. And what it is used for, it's used to calculate the activation energy of a simple reaction. So it's really not that complicated. You'd have to be given A, but it's just a calculation. Again, if you guys take chemistry beyond our class, you would get into it, but it's not on it's not in our class. It's not on our test. It's not on the AP test. So we're going to just skip it and move ahead. Okay, next thing is so we talked about activation energy diagram. Now reaction mechanisms. Okay, so what we're going to have here is we're going to have a series of steps. And we're going to, something that's in those series of steps that's on the left of the reaction in one step, and it's on the right in another step, we're going to be able to cancel it out. We have done that. We have done that before. We did that when we were doing half reactions back, I think it was in chapter 4, redox reactions. We did it in chapter 6. One of the ways we solved for delta H was the law of summations. We just added reactions up. So you have something common on the right and the left, we canceled out. Now here is some vocabulary, and the best, and this is not in the notes, so I'm going to write this on the board. This comes, again, from that science teacher up in Montana, Boltzmann, Montana, but just some of the vocabulary that goes with reaction mechanisms. So I'm just going to write this on the board. So elementary reactions, I thought this was the best way to put it. And what is key here is these things called unimolecular, bimolecular, and termolecular. So first of all, the collision theory. Okay, so remember, for a reaction to occur, 2 molecules had to collide. So number 1, the molecules had to collide. Number 2, they have to have the activation energy. If the collision does not have this minimum amount of energy, the reaction will not occur. And the molecules also have to be oriented correctly. And that's one. Again, we didn't really get to this last spring because of all that was going on. But usually in first year Chem, we really emphasize 1 and 2. But in AP Chem, you got to watch out for this one too. Okay, so there's 3 possibilities. The first one is where you just have 1 molecule. I'll show you what I mean by that. This would be called unimolecular. And really, this is the whole point of this what I'm writing on the board. So this right here, unimolecular. And an example of this would just be A going to the products. A great example of this is radioactive decay. This again is something in a normal year, normal chemistry class. I always talk about this, radioactive decay in May, the last couple of weeks of school. But all the elements 82 and after, and some of the elements before 82, lead's kind of dividing line, they're all radioactive, which means they just spontaneously decay. And that's what we're talking about here. So if we wrote out the rate law here, it would be K is equal to A to the first. This would be a first order reaction. Okay, but again, the vocabulary here, unimolecular. Okay, so we have two molecules. It would be bimolecular. Makes sense. One molecule unimolecular, two molecules bimolecular. And so here's two possibilities. One would be this, A plus A makes the products. So then the rate would equal K times A squared. Or we could have this, A plus B makes the products. I'll slow down here. So here rate would equal K times A to the first, B to the first. Both of these would be second order. But again, the key thing here is if a problem says bimolecular, we have two molecules colliding. Okay, and the third possibility are three molecules. So you think about three molecules colliding, having the minimum amount of energy and oriented correctly. It's not going to happen very often. This would be very rare. Not going to have three molecules do that all at once. This is called termolecular. So again, that's the vocabulary here. And this would be third order. And kind of the whole point of this map is these terms unimolecular, bimolecular, termolecular. Hopefully those kind of make sense from just the prefixes. Okay, so let me put up the rest of this slide, and then like I said, I wanted to give you guys just some time to ask questions. But what's here at the bottom? So the mechanism, what the mechanism is, it's a series of steps. It's a series of steps in the reaction. And we're going to do more of these tomorrow. And I don't know if it's hard, but it's just good to do them. So if you look at this reaction, again, we'll do more of these tomorrow, but just like, again, when we were doing the half reactions, you can remember that when we were doing the law of summations, when we wrote out a series of reactions, if we had something on the left in one step, on the right on another step, we were able to cancel those out. Or we had something on the right versus the left, I cancel it out. And you can see here in the first step, NO2 is on the left. And in the second step, NO2 is on the right, so they cancel out. They're not in the overall reaction. NO3 is on the right in the first step, but it's on the left on the second step, so it cancels out. So you cancel out all those that are on the left in one step, the right in another, and then you add everything up that you haven't canceled out. So NO2 plus CO are on the right, haven't been canceled out. And then on the right, the NO and the CO2 haven't been canceled out. And again, here's some vocabulary. So write the mechanism for this overall, or where the mechanism. So you're given the steps. And it says the intermediate. This is something I'm hoping to talk about tomorrow. An intermediate is something that's produced in a beginning step, which in this case is NO3. But it is then consumed in a later step. And I'm going to talk about this tomorrow. So that's an intermediate. We're going to compare an intermediate to a catalyst. And again, note the vocabulary. The first elementary step, the second elementary step, and the overall equation. And what we're going to do tomorrow is we're going to do these. We're going to kind of connect those to activation energy diagrams. And we're going to talk about the slow step and the fast step. A slow step, for me, or a good example of that, is like I live over kind of on the west side of Highlands Ranch, over kind of by the golf course over there, Highlands Ranch Golf Course. So a lot of times if I'm going up to the city, I go up Santa Fe, and always right around ACC, Arapahoe Community College, there's a series of lights. You know what I'm talking about, Carson? And I know if I can get through those series of lights fast, I'll be able to get to where I want to go fast. But if there's a lot of traffic, it takes a lot of time. That's the slow step, and that determines the rate. And I'm going to talk about that more tomorrow. But I'm going to stop there. I'm going to put up the next slide. But for those of you at home, I'm done with you. If you want to stay on, you can. For those in the class, I have the key here. I'll come around and take any questions you guys have. So I'm done talking. I'll put up the next slide if you want to copy that, but that's where I'm going to start tomorrow.
Mr. Wood?
Yes.
I was just wondering if tomorrow works to make up my test because we didn't have school Thursday when I was supposed to.
Mia, what time were you thinking about?
Probably after school because I don't have any off periods.
Tomorrow after school is not good for me. Could you do Thursday?
I can do Thursday.
Yeah, I've got a dentist appointment I got to go to, and I've got to leave here before school's out, like about 2:30. So can we do Thursday then?
Yeah, that works perfect. Sorry for all like the delays and everything.
I know it's been so weird. I know we were going to do Thursday, and then it was a snow day and everything.
It's all crazy.
I'm sorry about tomorrow, but I've had this dental work done.
No, it's okay.
We'll do it Thursday.
Okay, perfect. Thank you.
See you, Mia.
Bye.
Yeah, go ahead, Joe. Okay, you have some questions for me? Or are you going to look at that, Rex?
Yeah, I'm going to look at this and then I'll ask you
Okay.
questions. I don't understand like half the stuff on this quiz, to be honest.
Okay, we can look at it. We still have a little bit more to go. That's why maybe making this due Monday, Tuesday might not be a bad idea.
How come oh my god, I'm stupid. Never mind that.
Okay, so the key is that you saw it.
Yeah.
You doing okay there, Warwick?
Yeah.
So remember, the number one thing we did was the difference in charge. Okay. Second thing is the size. So if you look at this one, MGS is the biggest difference in charge. This is plus 1 minus 2. It's going to have the biggest size. Then in distinguishing these two, remember we said the smaller they are, that meant that the ions were closer to each other. And see all of those balls.
Yeah, I got it backwards. I don't know why.
Does that make sense?
Yeah, and then the other question I have is, I think you forgot to add my.
Okay.
Trying to get it. I think it's good.
Right, you doing all right, buddy? You. Young lady.
Yeah.
Liza, how you doing?
I'm doing all right, Mr. Wood. Mr. Wood, you didn't tell us jokes today.
You know, I thought with the events of the weekend, it wasn't
That's
a
all
joke. I
right.
will tomorrow.
I'll be waiting.
I just, I thought about it, and I thought, I don't think today's a good joke day. Jordan, you doing all right, my friend?
You Jim? But yeah.
I'm doing okay. Man, I had my first shot this weekend. Man, I didn't feel that good
Yeah.
for a couple of days there. I feel much better today, but man, I can say.
Even if you don't get like a reaction, it's not going to be the most fun.
You know, it was the weirdest thing because I had the virus and I've had antibodies. I told you this. I've given blood 3 times. And I thought that might mean my body wouldn't affect it all, but I was together with some friends and one of them's a doctor. And she said, no, because you've got the antibodies, your body knows how to fight. And so when they inject you with that stuff, your body said, okay, we're going to fight again. And man, I would say I was kind of knocked out.
Same thing happened to my mom.
Did she get after the first one?
Yeah.
Yeah, I would say both Saturday and Sunday. And see, my next one is Saturday before we come back from spring break. So that Monday, I might be a little loopy. I might be.
Well, my mom got her second shot already, and she couldn't work the next day.
How about the first one?
The first one she was mostly fine. The second one, like, really.
Well, see, if the first one knocked me down for a couple of days, the second one's probably gonna.
That makes sense. 'Cause the second one's going to be a booster.
Yeah.
The first one's kind of to prep you.
Which
to
one did you get?
Make it easier to
The
fight
Pfizer
the second
or
one.
Moderna?
I got the Pfizer one.
The Moderna one sucks more, but
It's a little bit worse.
yeah,
I'm
the Pfizer,
by the time you get it, the Johnson comes really good because I only get one.
I'm getting mine probably.
Well, you know, it's weird. It's like I had the virus back at spring break last year.
Yeah, I think I had it too. I didn't know.
But I didn't know it at the time. It's kind of a long story. I didn't know it until my oral surgeon, who's an MD, who's actually, that's where I'm going tomorrow, and I can't do Mia's test because I got to go see him. But I had it in March. I thought it was because of antibiotics. But he goes in May after I'm fine. He said, well, I think you need to go get checked. And sure enough, I had the antibodies. But my symptoms this weekend were exactly the same as the virus. Exactly the same. I mean, I was tired. I had, like at night, I would wake up and sweat. I had no appetite. I lost a couple of pounds this weekend just because I had no appetite.
Did you have a fever?
I had a fever some, and then I took Advil a couple times, which helped. So maybe that Monday we come back from spring break, I'll take some Advil in the morning and just get out of here. Because the second one will probably be, your second one knocked your mom down for a day.
Yeah, my dad let me in. But yeah, she said that like, she wasn't expecting it to be very bad, so she was like fine. Then got up the next morning, didn't feel great. She was like, I'm just gonna go to work anyway. And like an hour later, she was back home. She was like, all right, she had a fever. So,
Did she take Advil, do you think?
yeah.
Yeah, it was a doozy, that's for sure. Well, it'll be good. You just get it over with and then can move on. Okay, Rex, you said some problems from the book.
I have a whole bunch of questions.
Let's do it.
A whole bunch of stuff. Okay, first one is 29 of chapter 12.
Okay.
Like, mainly my question is, how do I distinguish between when I want to use the integrated rate law and the differential rate law?
Okay, so when they give you, Rex, this is how stupid I am, but this is how I remember it. So it's alphabetically. So when you do concentration versus rate versus concentration versus time. So when you do, they're both concentration, but the differential rate law, so a D versus an I, differential integrated. So the D is concentration versus rate, where integrated rate law is concentration versus time. So I think of alphabetical. So differential would be concentration versus rate. Does that make sense at all to
that
you?
makes sense.
And then the integrated rate law would be concentration versus time. So I'm looking here, since this is about time, this is going to be the integrated rate law. And so this means you're going to do graphs. So you're going to have to graph. So you're going to have to find the ln of the H2O2, and you're going to have to find 1 over the H2O2, and you're going to graph all three. And when you do that, I think it comes out to be first order, because what gives the straight line is the ln versus time.
That's not small.
Right.
It looks like.
Another big hint there too, Rex, if you look at this at the bottom. So they say determine the rate law, the integrated rate law, the value of the rate constant. But then it says, this is just a hint for you, when it says calculate the H2O2 at 4,000 seconds. When they're asking that, that is that ln AT equals negative KT plus ln A0. That is off the formula sheet. When they're asking that, when they're asking that last question, they're talking about this equation here. And this is connected to the integrated rate law. And so that to me would have been a huge hint that this had, because that's first order. This is new stuff for sure. Chapter 12, more than any other chapter, has a bunch of new stuff.
Yeah.
But the way you could have done this is you could have, yeah, we could have went back and we could do the graphs. And then once you know the graph, once you do the graphs, then Rex, then you, to answer that last question, then you would have done that equation I just showed you about the ln AT equals negative KT plus ln A0. Does that make sense? What you're saying, and it's a legitimately really good question, is how do I know? And the bottom line, because it's concentration versus time.
Okay. And then, all right, what about 31?
It's going to be the same thing, yeah.
Okay.
So determine the rate law, the integrated rate law, and the value of the rate constant. So yeah, you would have done graphs. And, I mean, the key is that you know how to do it. And then see, there again, at the last thing, it says calculate the NO2 at 2.70 times 10 to the 4th seconds. So that again is telling me this is probably first order, because that LNAT equals negative KT plus LNA0 is only for first order. But this one I'm looking, no, not first order. So this is second order. So then it would have been.
Could we work this problem? Because I'm kind of confused when it wants.
Yeah, let's do it.
Rate laws.
Let's look at what they've got here. Because it would be a lot of work, because you're asking really good questions. So what I would have done first here, Rex, is I would have done graphs. So I would have. So see, what they did is they took. So this was given.
Mm-hmm.
So then they just used their calculator. They took the ln of those. Then here they just took the reciprocal of those.
Mm-hmm.
And then they went and they graphed them all. And so the straight line relationship was the reciprocal versus
second
time.
order.
So
Yeah.
second order. And then when it's second order then, which is really, to be honest with you, not that often, but when it's second order, then this is going to be the equation that we're going to use.
Mm-hmm. Okay.
So
and then to find the rate laws.
So it would have been the rate law, it would have been second order.
Okay.
And then this would have been the integrated rate law for second order.
Okay.
Which is on the formula sheet.
Mm-hmm. Okay.
Does that make sense? Because you're asking a good question. The key is that what I see what you're saying is good is how can you tell this from what has been given to you? Does that help a little bit?
Yeah.
Hey, see you guys. See you guys on the
See you Wednesday,
computer
Mr.
tomorrow. See you, Tyler.
And then,
See you, Lexi. Have a good day.
to find the rate constant. I mean, I guess I could plug in.
Then the
how many
rate
is the
constant,
half-life.
the rate constant would be the slope of that line.
Okay. Gotcha.
These are great
Is
questions.
this gonna be like on the test?
Something like that. I think, well, look at the quiz. Like the quiz, like Rex, if you look at this one right here. So here, and then I wanted you to graph the first order, second order. So that means I would have done graph of time versus that and that. And look for the seconds. Hey, see you, Laura. Have a good day. So what would have been the straight line is that versus time. And then the rate constant would have just been the slope of that line. So this problem is exactly like 31.
Okay.
See you, Jack.
All right. Well, yeah. I actually did that question. Because I did it where I like